Hi, I'm Jim Price, VP of Engineering at Corry Micronics. I'm here to talk to you today about bandpass filters. They're very often used in a lot of communication systems, and there's a lot of considerations to think about when you're selecting the best technology to use for a bandpass filter, and I plan to go over a few of those today. Bandpass filters are used in a lot of different applications. Most typically, communication systems use them. And just as the name sounds, it's used to pass a certain band of frequencies while rejecting other bands of frequencies. I'm going to go over some of the different types of bandpass filters and some of the different methods of implementing them, how to choose the best filter, what the trade-offs are, and some of the best technologies to use to achieve these filters. I also will go over why you'd want to use one technology over the other, what the advantages and disadvantages of each are, and tell you a little bit about the company I work for, Corry Micronics. And of course, at the end, you can always ask some questions of me. All right. So as I said, bandpass filters will allow certain frequency bands to pass while rejecting others. And a typical application for something like that would be in a communication system where you are trying to transmit signals out on an antenna, and the amplifier that you're using to boost the power up might have some harmonic distortion or intermodulation distortion in the signal. And if without a filter there, you could spray information over a part of the frequency spectrum that you don't want to contaminate. Also, in the reverse direction, if you're using them in a receive situation, a lot of times there can be interfering carriers that you pick up on your antenna, and they can overwhelm your low noise amplifier. You don't want that to happen either, and bandpass filters are perfect for preventing that from happening. So here's a graphical display of that. Bandpass filter is shown after an amplifier in the case where you're using a power amplifier to transmit. And bandpass filter can be also used on the receive side. Typically, they handle very different power levels, but the selectivity of the frequencies is the same. When you design a filter, any kind of a filter, a lot of times you'll start with a table. You'll select the type of filter that you want, the type of response that you want. Chevy, Chef, Butterworth are some examples, Gaussian, that kind of thing. And you can use tables that will give you the numbers that you can use to generate typically the inductive and capacitive component values that you need to create that style of filter. Now, lumped element filters or LC filters are what a lot of people think of when or they think of creating a filter design, but that's not the only way to create a filter. You don't have to use inductors and capacitors. There's other filter elements that you can use that might be better suited to your application. And I can go through a few of those as we progress. Now, here's an example of a filter table. You might have seen something like this. This is for a Butterworth filter, it looks like. And here are shown either a 3-pole or a 2-pole filter, and the different filter values that you would use depending on what you're trying to achieve or what kind of frequencies and impedances that you're up against here. And you basically plug these numbers into some standard equations, and you'll come up with inductor and capacitor values, and you'll get a filter that has the theoretical frequency response you're looking for if the filter elements were perfect, which of course they won't be. So that leads us to picking the best technology for your filter. Let's just say that you wanted to create a filter that required a 5-pole response that had a 50 megahertz bandwidth at 1 gigahertz. You could implement that with a standard LC filter, as I've just shown, or you could go with a cavity filter, a comb filter, strip line, microstrip filters, ceramic coaxial filters, helical filters, and even other filter styles that I'm not mentioning here. could possibly do that for you. And each one of those has certain advantages and disadvantages over an LC or lumped element filter. Yeah, shown here are a few different types of filters that I had just mentioned. The LC filter is shown, and of course, that's just a circuit board with inductors and capacitors soldered to it. There's also a microstrip filter here, and that's a circuit board with just traces printed on it. Helical filter is coils grounded on one end and floating in the air on the other end, and they act as more as quarter wavelength resonators than as inductors, and so their quality factor or the performance is a little bit better than a typical LC or inductive style filter. And then you also have coaxial resonator filters, which consists of a high permittivity material that's shaped like a coaxial cable. And those resonators that I'm showing in this picture are quarter wavelength long. This is a little chart I came up with that is roughly shows what some of the trade-offs are between the different filter styles. LC filters typically have a quality factor that's fairly low. It's one of the provides you with one of the worst insertion losses of all the different filter types. Quality factor is a way to identify the suitability of the elements of the filter that you're using for filtering purposes. The higher the number, the more ideal the component is. And the number like a 50 to 200 range, like an LC filter has, is fairly low. As you can see, cavity filters can approach quality factors of 5,000. So can comb filters. Microstrip and strip line filters are fairly low. Ceramic coaxial resonator filters do a little bit better. Helical filters aren't too bad. And dielectric resonator filters have some of the highest Qs possible, but they have other trade-offs that you have to consider when you design with those. Shown here is a physical implementation of a comb or a cavity style filter. These consist of rods that are quarter wavelength long in a housing, and the rods couple energy to each other depending upon how close the rods are to each other. The closer the rods are to each other, the more energy is coupled from rod to rod, and the broader the bandwidth of the filter. As you can see in this example on the right picture, the rods have small spacer rods in between them that serve to limit some of the energy that is passed from rod to rod, and that allows you to tune the bandwidth of the filter and give you a lot of control over the performance of the filter during manufacture. These filters are typically very good, as you can imagine, for high power because they're very low loss, and they're made out of solid metal, so they can take a lot of power and they can dissipate heat very well. So here's a HFSS simulation of a comb filter. This is a typical model that you could use to simulate these things. This shows the quarter wavelength rods grounded on the far end and floating in space on the other end with a tuning element entering the top of the rod to tune the center frequency of each rod. And then, of course, there are tuning elements between the rods to adjust how much energy is coupled from rod to rod. And if you do this correctly, you can get a frequency response similar to the one that's shown in this picture, where you have a fairly flat, broad top with low insertion loss and very good skirts for rejection. Now, a quarter wavelength resonant filter electrically looks like an inductor in parallel with the capacitor. The rod itself looks like an inductor in parallel with the cap, and if you couple energy into the rod or into the inductor in parallel with the cap, you get a frequency response similar to what is shown in this this picture. The peakier and the spikier that picture is, the higher the quality factor of the elements. So typically, a quarter wavelength rod will look pretty good. It'll be a very narrow, spiky sort of a graph there. And an LC filter will be much broader because the quality factor won't be nearly as high as the rod. As I was saying before, the rod can approach 5,000 quality factor, whereas you're lucky with an inductor or cap to get 200 or 300. Now, if you make the rod a half wavelength long, you get a different filter element, and that's more like an inductor in series with a capacitor, and you can actually get a notching function out of that. And the steepness of the notch is also dependent on the quality factor of the elements that you use. The notch gets deeper and narrower the higher the quality factor of the elements. So typically, an inductor and a capacitor would not have nearly as deep and as narrow a notch as a half wavelength rod would. So this is an example of a 5-pole bandpass filter. It's 5-pole because there's 5 rods here. And one thing that, talking about trade-offs between different kind of filter elements, when you use high quality factor materials like this and you create quarter wavelength rods, the voltage at the top of the rod can exceed the voltage that you would expect to get in the filter. For example, a 100-watt signal would typically have a peak voltage of 100 volts at 50 ohms. But because these rods are extremely high impedance and high quality factor, the top of each rod can get to voltages much, much higher than that. In this example, and it varies depending on the type of filter you have, whether it be Chevy Chef or Gaussian or whatever you're using, and the exact length of the rods and the exact quality factor of the rods. This can vary quite a bit, but in this particular example, I simulated this filter, and the voltage at the top of the second rod was over 500 volts, whereas you wouldn't expect it normally to be over 100 volts. And this would be of concern if you were at high altitude and you were worried about breakdown voltage from the top of the rod to the grounded case of the enclosure that the rod is enclosed in. So you have to be careful when you design with filters like this and what some of the limitations are. And these cavity filters can have high voltages at the top of the rods, and they can arc at higher altitudes. So you have to design for that. There's ways around that. You can still use these at high altitudes. You just have to be very, very cognizant of your rod spacings. So as I said, you have to be aware of voltage multiplication in a lot of these coupled resonator style filter designs. The peak voltage can get very, very high, and but that's also part of the charm of it as well, because when the voltage does get very high, that means you have a high quality factor, low insertion loss, and good performance in the filter. It's going to approximate the theoretical much, much better. The rejection skirts are going to look more like an exact Chevy Chef, if that's what you're going for, than it would be if the quality factor was lower. Now here's an example of a triplexer. Now triplexer is just 3 different bandpass filters in the same housing. They're tied together on the left side here to a common port. That would be typically an antenna port. And on the right, you have low, mid, and high band connectors that will allow you to multiplex different frequency bands onto the same antenna, assuming the antenna bandwidth is wide enough to handle that. Each one of these filters is a bandpass filter. The lowest frequency band is the one at the bottom of the screen, and you can see that because the rods are all about the same height, so you would expect the filter, each of these filters, to be about the same frequency, except the rods at the bottom have a lot more capacitance to the lid, and that lowers the frequency. The ones in the middle have not as much capacitance to the lid, and the ones on the top side have somewhere in between. So that would be the mid band. So the mid band would be the top channel, the low band would be the bottom channel, and the high band would be the middle channel in this particular example. It doesn't have to be that way. They could be rearranged, obviously, but that's the way it is in this example. So shown here is the frequency response of the triplexer. The upper left is the low band response. The lower left is the mid-band response, and the right is the high-band response. You can see that there's some fairly beautiful looking bandpass filters there, just very close to ideal. And that's because the quality factor of this filter is very high. You can never achieve these kind of results with an LC filter, but it's not too difficult when you're using a transmission line filter like this. Now, the one downside of transmission line filters is that they do repeat at higher frequencies, and that's what you're seeing to the right of each of these plots. Those are higher frequencies, and these rods don't just resonate at 1/4 wavelength. They'll resonate at 3/4 wavelengths, and et cetera, up into the frequency spectrum. They'll keep resonating and re-resonating as you go higher and higher in frequency. And the only way to get rid of that, if you don't want it, and a lot of times you don't want it, would be to put these in series with a low-pass filter. The low-pass filter could knock some of that out, and a low-pass filter won't have to have as high Q requirements because you're not really trying to achieve the peakiness that you see in these filters. The low pass filter can have a much gentler roll off because you're discriminating from something that's very low in frequency versus something that's very high in frequency. So you have a lot of room to get the rejection down, and the insertion loss can stay very good, even though it's an LC filter. LC filters are actually kind of perfect for cleaning up things like this because they tend to not repeat over frequency. Some of the key takeaways of this are that you can use different style filters to achieve different design results or performance results. If you want best insertion loss, you might want to use a cavity or a comb filter. Same with power handling. Now, size and weight are where cavity and comb filters let you down. LC filters are much, much smaller and lighter than cavity and comb filters. They don't have all that metal. Bandwidth is another consideration. One thing I didn't bring up before about the transmission line filters are that their bandwidth characteristics can be somewhat limited. You can't make them extremely broad band because the bandwidth is dependent upon the closeness of the rods. You can only get the rods so close together to achieve the bandwidth that you want. You can achieve maybe a 50% bandwidth on a cavity or a comb filter, and by that I mean if your center frequency is 1 gigahertz, you'd be very lucky to get 500 megahertz bandwidth, 50% of that. It's just not easy to get the rods close enough together to get the wide bandwidth to couple enough energy from rod to rod to make that happen. Whereas with an LC filter, there's really no practical limitation. You can make them as wide a bandwidth as you need. They can follow theoretical bandwidth limits for any kind of a filter. It's just that their quality factor performance isn't the greatest, neither is their power handling. So there are always trade-offs. And again, as I said, with the transmission line filters, you have re-entry. They resonate and re-resonate at higher frequencies, and that's definitely a big downside of those. But they are easy to tune, relatively easy to tune and control. And so you can achieve really good return loss with those. It's hard to get great return loss with LC filters a lot of times because you can't infinitely tune the elements. Whereas you can do that with cavity and comb filters. You can design in tuning screws that allow you to make very fine adjustments to those different parameters to get the filter exactly tuned in as you want it to be. Now, as I said, Corry Micronics has been around for a long time, and we manufacture a lot of RF and microwave components. We have over 50 years of experience, and we have our own machine shop. So when it comes to a lot of these filter types that I've mentioned, we can machine them and build them in-house. We have complete control over the quality and the tolerances involved. Furthermore, different components we design besides filters, we make switches, diplexers, multiplexers, splitters, combiners, and we can combine them together into RF subsystems. For example, if you combine switches and filters, you can create something called a switch filter bank, where you can switch different bandpass filters into your design depending upon what your requirements are. You could have many different bandpass filters in one package and only elect to use the filter that you want at any given time through switching. We also make some of our legacy products, our bolt-in and solder-in RF feed-throughs. They're a great option for filtering connectors and I/O ports. As I said, if we combine some of the different capabilities we have, amplifier design, switch design, filter design, we can create many different kinds of subsystems and systems for customers and meet a lot of different interesting requirements. Now, I know I went through a lot. Does anybody have any questions?
All right, first question I have. Transmission line filters can have much higher Qs than LC filters. What are the disadvantages of transmission line filters relative to LC filters?
There are a couple disadvantages. The one, as I had mentioned in the presentation, is that they tend to repeat over frequency. So transmission line filters will resonate and re-resonate at higher frequencies. So you'll get additional pass bands beyond your original lower frequency pass band. And a lot of times that's very undesirable. Sometimes you don't care. Sometimes all you really need to do is excuse me, is pass a band of frequencies and knock out or reject frequencies near that band. But if you need to reject frequencies out across the entire spectrum, they're not the way to go, because they're going to repeat over frequency and re-resonate. Another disadvantage of transmission line filters is they can become quite large at lower frequencies, because they're wavelength based design. Lower frequencies are longer wavelengths, so the elements can get large. So if you're sub a few hundred megahertz, you generally want to stick with LC filters or something like that to avoid that problem, the size and weight problem.
Why are inductors and capacitors problematic in filter designs, and how do you design around their constraints?
The problem mostly with inductors is their quality factor is fairly low. You're doing well to get quality factors of 200 and 300 out of an inductor. And there are other filtering methods that'll allow you to get quality factors into the thousands. And anytime you limit the quality factor of your components, you're limiting their suitability for an ideal filter response. A lower quality factor is going to cause higher insertion loss and poor rejection, less than theoretical anyway. Of course, maybe that's okay. It depends what your insertion loss requirements are and what your rejection requirements are. LC filters are used all the time, and they can adequately create good filters. It's just it depends on what your ultimate requirements are and your goals are. They are good for lower size and weight. They're very small and lightweight, so that is one advantage of LC filters. So I don't want to make them sound too bad, but they're generally not the first tool you go to when you need low insertion loss or high rejection.
When designing a filter, do you use the same approach for both the transmit and the receive signal paths, or are there considerations you need to take depending on which input side you are working?
Yeah, it's pretty much use the same. The only consideration is a lot of times when you're transmitting, you're in a higher power situation, so that might ultimately determine the type of technology that you want to use. You might need something that's lower insertion loss, because at higher power levels, low insertion loss is less heat, and that's often a consideration. But really, other than power, the transmit and receive filters have the same design philosophies.